Hi, everyone. So today we're going to be talking about Chapter 7, Cosets and Lagrange's Theorem. So what is a coset? Well, let H be a subset of a group G. We're going to define this symbol AH to be all elements of the form A times H, where H is in the subset and A, of course, is some other element in the group. Same thing here, HA. Anything looks like that. Okay, then this conjugation sort of set here, A big H, A upper inverse. Okay, looks like that. All right. If H is a subgroup of G, then we say the symbol AH is the left coset, left because the little a is on the left of the symbol capital H. Left coset of H containing what's called the coset representative A. So coset representative A because it's AH. And you can say, well, right coset here. So for example, let's let G be the dihedral group D4. And I'm going to use some notation here coming from chapter 26, I think it is. Let me make sure that's, yeah, from generators and relations. So we know that, and this isn't totally right because I don't have relations here, but we know that D4 can be thought of as a subset of the symmetric group S4 generated by, well, a permutation that takes all of the vertices of a square and permutes them by doing it going 90 degrees that way. So the 1 goes to the 2 position, 2 goes to 3 position, 3 goes like that. Okay, so that's a permutation. Then there's, so that's our like rotation we said before, and our reflection here takes 1, 2, 3, 4, and I'm gonna, that's like what we used to call the vertical one, I guess, the way I've drawn it. It's gonna flip the 1 and 2 and the 3 and the 4. So if you have, and we did a homework problem, I think, where you can show that all elements in D sub n are determined as a product of some power of this rotation and some power of this reflection, okay, or a reflection like this. So I'm going to take H1 to be this subset, which actually is a subgroup, right? And this is another subgroup. Note that this element here is in a generator, right? So what are we going to do here with the cosets of those? And note that these are how elements can be written, okay? So this is a homework problem. And the question is, why don't we have to consider elements of the form where we switch that? Well, because there's a relation that says, okay, 1, 2, 3, 4 to the j, 1, 2, 3, 4, all to the I is the same as 1, 2, 3, 4 to the I, 1, 2, 3, 4 to the d4 minus j, that's if I is 1. And it's just the same thing, right? 1, 2, 3, 4. 1, 2, 3, 4, 0 to the 0. I'm shooting a video. Go away. Sorry about that. 1, 2, 3, 4. The j, nothing changes if I equals 0. So we can always write anything of this form into the other form where we have the reflection at the first. Okay. So how do you find all the cosets? Well, you just have to actually write them all down, right? So you take all the elements of D4. So D4 consists of all elements. So E, then 1, 2, 3, 4, then 1, 2, 3, 4. And the reflection once, then twice, and there's eight of these, right? And then we got just the powers of the rotation. Oh, well, I guess I didn't need to do all that, did I? I can write them all down. Let's just write them all down. Okay, that's 1, 2, 3, 4, 5, 6, 7. I'm missing one. Wait. 1, 2, 3, 4, 5, 6, 7. Oh, I don't have. There we go. Okay, so first look at EH1. Well, that's just H1, right? 1, 2, 3, 4 times H1 is equal to, we get 1, 2, 3, 4 E, and then 1, 2, 3, 4 squared. Turns out that this just is H1 again, okay? Then more interesting ones would be, say, 1, 2, 3, 4 times H1, and that's going to be 1, 2, 3, 4, and then this rotation times the reflection, 1, 2, 3, 4. Which we already said was equal to 2, 3, 4. Then this is 1 goes to 2, which goes to 3. No, I could just switch it over. Yeah, let's do that. So it's 1, 2, 3, 4. 1, 2, 3, 4 cubed. Okay, so when I switch this to the other side, it takes this power and subtracts that from 4. And what do you get? Anyway, you get another set, some set, okay? Let's do so this, okay, then this times this one, which should be 1 goes to 2, or, well, okay, I'm going to go ahead and do some things in my head here. So if I switch the 1, 2, 3, 4, the rotation, and the reflection, then this becomes 1, 2, 3, 4, and then a cubed, and then I get 1, 2, 3, 4 all squared. Okay, with 1, 2, 3, 4 cubed. So what do I get? I get reflection, rotation, then rotation cubed. Okay. Anyway, I get, it turns out there are only 4 distinct cosets. Okay, so let me see. So far I've got so I've got this one. So let's see, let me make sure I've got some. Okay, H1's a coset. Then I've got this thing, which is also H1. And I've got this one, which is different. Then I've got another one. I could call this like something else. I don't know. Or, well, yeah, I can just use say this is the symbol. This is the coset representative, represented by the reflection, right? 1, 2, 3, 4, or the rotation, I mean. Then I've got the other one here, which we saw was different. And there should be one more. So if I try, say, 2, 3, 1, 4, H1, that will give me a different answer. Okay, I know it's different because this one this one has this reflection, and this would have that reflection. They're going to be different. This and this are not the same. This and this are not the same. So there are 4 different ones. And you might need to check that that's the case, but it's true. Certainly, if I do the same thing for H2 and we get a complete set of representatives coset representatives is a set of 4 elements. I don't know, maybe I should say a complete set of cosets would be something like EH2, then probably 1, 2, 3, 4 H2, and then 1, 2, 3, 4 H2. Okay. And I'm not so sure, but maybe this could be right. Okay. I can check. Let's see. This times the identity is just this again. This times, what do we got here? 1, 3, 2, 4. So 1 goes to 3, which goes to 4. 4 goes to 2, which goes to 3. 3 goes to 1, which goes to 2. Okay, so it's 2 rotations. Is that the same as this one? So we're just going to spot check here. So this guy here, if we write it out as a 1 goes to 2, which goes back to 1, okay. 2 goes to 3, which goes to 4. 3 goes to 4, which goes to 3. Wait a minute. 1 goes to 2. Oh, sorry, I didn't. Forgot to do. Yeah, I got to do this thing times e. So 1 goes to 2, which goes back to 1. 2 goes to 3, which goes to 4. 4 goes to 1, which goes to 2. All right. 3 goes to 4, which goes to 3. So you just get this thing. Okay. That can't be right. I made a mistake somewhere. One goes to 2. Which goes back to 1. Can't be. Oh, yeah. Oh, no. Sorry, this is a diagonal. Yeah. Okay. No, this is right. And then this times yeah. So this is the symmetry. The diagonal, right? Okay. Sorry. 1, 3, 2, 4. Okay. So 1 goes to 3. 3 goes to 1. 2 goes to 4, which goes to, yeah, so that would be the other diagonal. Okay. That makes sense. Okay. So that is not the same as that. Anyway, I've spent enough time on this, I hope. Okay. So let's talk about some properties of cosets before we get too far into the weeds here. If H is a subgroup, so it's always going to contain the identity, right? So a coset represented by A will always contain A. Also, if you notice here, right, if I took the coset with the representative that was actually in the subgroup, I always got the same subgroup back. Most cosets are not subgroups, right? So that notice everything except for H2 and H1, which are definitely cosets, right, represented by the identity, right, E, H1. All these other ones are not closed sets. They don't contain the identity. They don't have inverses necessarily. So they're not subgroups, right? So the only subgroup is that the only coset that is a subgroup is the subgroup itself. And we can prove this. So if AH is H, that implies that A is in H, right, from part 1. Okay. And so that's from part 1. Okay. To the other, if A is in H, right, then that means that AH to show they both are contained in one another, right? So if I let G be in H, then A and G are both in H, which means that AG is in H since it's closed. Okay. Or wait, sorry. I can say it this way. A is in H, so A inverse in it is in H, which means that A inverse is in AH, right? Since this is an H. That's the identity, right? Which means that A times A inverse G, right? So not only that, let me say it this way. Yeah, more importantly, A inverse is an H, so let's just say it this way. A inverse all right, A inverse G is in H. So A inverse G is in AH, right? Okay. That means that G is in the coset. Which means that H is a subset of the coset. Okay. So if I take something in the coset, since A is in H, right? A little h is in H as well, which means the coset is a subset of the subgroup as well. Okay, so that shows that they are equal. All right. If we follow this argument another way, okay, then if we have two coset representatives that give the same set, that's if and only if one of those representatives would be in the other coset. It's I mean, if you think about, right, this is true, means A, and AH equals EH, if and only if A is in H. You can do a similar rigmarole with this guy. Okay, so if A, first of all, all right, the first direction is very simple, right? So this way is easy. Okay. And maybe I should have done this up here. For the reverse implication, we do a similar thing we just did. So A is in BH means that A is equal to B little h for some h, right? But B little h H inverse, right, would also be in, no, sorry, we want to show that so yeah, so take, yeah, we're going to take BH1, right, to be some other element in BH. And we want to show that it is contained in AH, right? Well, A is equal to BH, and H1 inverse H is in H. So that means that BH1 H1 inverse H is in BH. I already have that. Right, that's okay. Wait, my proofs are all screwed up here. Okay, let me think about this here. A is equal to BH. And so, yeah, all right. So that means that everything, all right, pardon me. Okay. So this means that everything right, everything in AH is of the form BH big H, right? But everything in there is equal to that, right? So this is from what is that, part 1? No, part 2. This is from number 2. All right. So that did it, actually. And because it's an if and only if in number 4, it says, okay, you either have two cosets are equal or they are completely disjoint. So, you know, if AH intersect BH is non-empty, that means there's some C in AH intersect BH. That means that's if and only if CH is equal to AH, right? And CH is equal to BH. Okay, so then AH is equal to BH, right? So this is saying that the cosets partition the elements of the group. Okay. Since, you know, to get a coset, you can take any coset representative as any element from the group G, right? And so you get cosets, right, that are for any element in G, it's in some coset, okay? And the cosets are not, they never overlap, right, unless they're equal. So you get a partition of the elements. This property here has to do with just kind of how do you read this equal sign. Well, you can, you know, or you could say, or A inverse B is in H if you wanted to sort of multiply on the left by A inverse on both sides. So this is probably more obvious, right? I mean, if AH equals BH, then that means that A little h is equal to B for some little h. Okay. So, well, let's think about it this way. If AH is equal to BH, okay, and so then this means that H is equal to A inverse B. Okay, so that's the easier thing to prove, right? But we could also say, well, but at the same time, H, right, so that must be in H. But then H inverse is equal to B A, sorry, let's do the, I'm going to do the pants thing, right? B, oh, I got to go the other way. So this also means that BH is equal to A for some H. And so that means that B inverse A is in H. right? But so is its inverse. Okay. All of the cosets have the same cardinality. They have all the same number of elements. So to prove this, we need to find a one-to-one correspondence. Okay. Oh, and let me say this one thing. So we've been using multiplicative notation for this. Okay. Note that's multiplicative notation. Additive notation is this. For cosets, which means that we could rewrite all these things in the same way, right? I mean, here you would say instead of A, B inverse, you'd say A minus B would be in H, for example. So in additive notation, you would say that. Okay. All right. What about this? We need a one-to-one correspondence between the elements in here and the elements in there. And we're just going to consider the mapping goes from here to there. That takes little AH and maps it to little BH. Okay, why is it one-to-one? Well, suppose well, yeah, one-to-one and onto. So it's onto is very obvious, right? Everything of here is of the form BH for some H in big H. Okay. So you definitely get every element there. Why is it one-to-one? So suppose AH1 is equal to AH2. Well, then left cancellation. Okay, so it gives you that H1 is equal to H2. And so that essentially is saying, or sorry, no. Oops. This should be B's, right? Right. So then, if say I have AH maps to BH1 and BH2, so there are two elements that are there are two different. So AH1 maps to BH1, AH2 maps to BH2, and they're equal. So suppose that there are two things in the range that were equal. Well, they'd have to be the same in the domain as well. Okay, so that's that here, just have to think about what this is saying. Okay, in the interest of time, I think I'm going to skip this because we're not going to be dealing with this conjugation coset very much yet. So let's skip this for now. See the textbook for this solution here if you want. And this is saying that a coset is a subgroup of G if and only if the coset representative is in H. Well, right, A is in H if and only if AH is equal to H, and so that is a subgroup, right? So that's that direction. This direction, AH is a subgroup, which means that a little h equals E for some H in H, which means that any element in, so suppose H little 1 is in H, then H little 1 is in the coset. That means that the subgroup is a subset of the coset, but certainly if you have anything, right, but you also have, but AH is a subgroup implies that E is equal to, wait, I've already done that one, that part. Okay, I need to show, take, all right, so now let let H is in a subset of G. I need to show that A is in H. Why was I showing this other bit? Well, okay. Yeah, no, I get it. So I'm going to show that AH equals H, and then, you know, A would be an H. Okay, so now let oh, but now we have cosets that have elements in common, right? I keep showing the same thing over and over again, but I could be using number 4. Therefore, A must be in H, right? So by number 1, right? Okay. Whew. So those are all the properties. Let's talk about our main theorem, and then I will prove it next time. So the main theorem of this chapter is called Lagrange's theorem. It says if G is a finite group and H is a subgroup, then the order of H divides the order of the group. Moreover, the number of distinct cosets would be equal to that quotient. And a corollary to that would be that the order of any element of a group must divide the order of the group if the group is finite. And so this is a pretty big deal, but this basically comes from all the work we just did with cosets and the fact that we get partitions. The number of distinct cosets is called the index. So the index would also be a divisor of the order of G, since it's this number. But we will get to that next time. So get started on reading this section, and I'll see you in a little bit.